On a quiet February morning in 2020, somewhere in a control room outside Canberra, Australia, a screen that had been talking to a spacecraft for over 4 decades suddenly went blank. No signal, no data, no confirmation that anything was even still out. There. For the engineers watching, this wasn't panic-inducing in the way a movie would show it. There was no siren, no red flashing light. Just silence. A very deliberate, very expected silence. But silence from Voyager 2 is never really nothing. Because when you are talking about a machine that is currently more than 20 billion kilometers from Earth, further than any human-made object has ever traveled, silence carries weight, it carries history, and it makes you ask a question that sounds almost childish, but is actually one of the most profound questions in the history of space exploration. Is it still out there, and is it still listening? To understand why that moment mattered, and why the story of Voyager 2 losing contact with Earth keeps resurfacing again and again, decade after decade, you have to go back to where this whole journey began. It starts in 1977, a year that, in hindsight, looks almost impossibly lucky. Every 176 years, the outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, line up in a way that allows a spacecraft to visit all 4 using a technique called gravity assist, essentially slingshotting from one planet to the next using their gravity instead of burning enormous amounts of fuel. NASA scientists realized this rare planetary alignment was happening in the late 1970s, and they weren't going to let it pass by. So on August 20th, 1977, from Cape Canaveral in Florida, a modest, refrigerator-sized spacecraft called Voyager 2 lifted off the launch pad. 16 days later, its twin, Voyager 1, launched on a faster, more direct trajectory toward Jupiter and Saturn. Voyager 2, launched first but positioned second, was given a longer, more looping path, one that would eventually let it become the only spacecraft in human history to visit all 4 gas and ice giants of our solar system. At the time, nobody expected these machines to last this long. The original mission was designed to last about 5 years. 5 years to fly past Jupiter and Saturn, take some pictures, gather some data, and then quietly become another piece of drifting hardware lost in the vacuum. Nobody planning this mission in 1977 seriously imagined that in the year 2026, these 2 machines would still be alive, still transmitting, still teaching us things about the universe that we could never learn any other way. And yet here we are. Voyager 2 first arrived at Jupiter in 1979. What it sent back changed planetary science overnight. Before Voyager 2 and its twin arrived, our understanding of Jupiter was based on blurry telescope images and educated guesses. Voyager 2 gave us close-up photographs of the planet's swirling storms, its faint rings that nobody knew existed, and its moons in a level of detail humanity had never seen before. It was Voyager 1, examining the data alongside its sister probe, that helped confirm active volcanoes on Jupiter's moon Io. The first time active volcanic activity had ever been observed anywhere beyond Earth. 2 years later, in 1981, Voyager 2 swept past Saturn, capturing the planet's rings in a level of structural complexity that stunned scientists. Where earlier images showed simple bands, Voyager 2 revealed thousands of individual ringlets, gaps, and braided structures that took years to fully explain. But it's what came after Saturn that truly set Voyager 2 apart from every other spacecraft ever built. Because after Saturn, mission planners made a decision that would define the rest of Voyager 2's legacy. Instead of ending the mission, they used Saturn's gravity to redirect Voyager 2 toward Uranus. In January 1986, Voyager 2 became the first, and to this day the only spacecraft to ever fly past Uranus. What it found there reshaped our understanding of ice giants completely. It discovered 10 new moons that no telescope on Earth had ever detected. It measured the planet's strange, almost sideways magnetic field, tilted at an odd angle relative to its rotation axis, a mystery scientists are still trying to fully explain. Then, using Uranus's gravity, Voyager 2 was slingshotted once more, this time toward Neptune, the most distant planet in our solar system. In August 1989, 12 years after launch, Voyager 2 became the only spacecraft in human history to visit Neptune. It discovered the Great Dark Spot, a storm system as massive and violent as Jupiter's famous Great Red Spot. It confirmed that Neptune, like Saturn and Uranus, has its own system of rings. It found 6 new moons, including Triton, an icy world with active geysers spewing nitrogen gas into space, a moon so strange that some scientists believe it may be a captured object from the distant Kuiper Belt rather than something that formed alongside Neptune itself. By the end of the Neptune flyby, Voyager 2 had done something no spacecraft before or since has managed to do. It had visited all 4 giant planets of our solar system in a single continuous mission. It is, quite literally, humanity's grand tour of the outer solar system, and it happened only once, using a planetary alignment that will not occur again for well over a century. And then, instead of shutting down, Voyager 2 kept going. It's easy to forget, when you're talking about spacecraft and orbital mechanics and gravity assists, that these missions were never just about engineering. They were about something much bigger. The idea that humanity might one day send a piece of itself beyond the solar system entirely. That's why, bolted to the side of both Voyager spacecraft, is something that has nothing to do with cameras or magnetometers or plasma detectors. It's a golden record, a physical analog phonograph disc containing sounds and images of Earth, greetings in 55 different languages, music from cultures across the globe, from the sound of thunder, of a mother's heartbeat, of whale song, of laughter. It was assembled under the direction of the astronomer Carl Sagan, with the understanding that the odds of anyone or anything ever finding it were astronomically small. But small odds were never really the point. The point was that we tried. That in 1977, a group of scientists decided that if humanity was going to send something into the void that might outlast our civilization, our sun, maybe even our species, it should carry with it not weapons, not warnings, but an offering, a hello. That golden record is still out there right now, attached to a spacecraft traveling at roughly 15 kilometers per second, more than 34,000 miles per hour, moving further away from us with every second that passes. In November of 2018, Voyager 2 crossed a threshold that very few things in human history have ever crossed. It left the heliosphere, the vast bubble of charged particles and magnetic fields blown outward by our sun, and entered interstellar space. This wasn't a symbolic boundary, it was a measurable one. Instruments on board detected a sudden sharp increase in cosmic ray levels and a corresponding drop in the solar wind particles that had surrounded the spacecraft its entire journey. In simple terms, Voyager 2 stepped outside our sun's bubble and into the space between stars. Its twin, Voyager 1, had made the same crossing 6 years earlier in 2012. To this day, these are the only two human-made objects that have ever operated in interstellar space. Not just reached it, operated in it, continuing to send back data from a region of the cosmos where no other spacecraft, past or present, has ever gone. This is where the story gets both more remarkable and more fragile, because now we return to the moment in February 2020 when Voyager 2 fell silent. The reason for that silence had nothing to do with the spacecraft itself. It had to do with something on Earth. Voyager 2's unusual trajectory, dipping below the plane of our solar system as it headed toward interstellar space, means that it can only be reached by antennas in the southern hemisphere. And there is only one dish on the entire planet capable of sending commands powerful enough to reach it. A 70-meter wide radio antenna called Deep Space Station 43, located just outside Canberra, Australia, and operated as part of NASA's Deep Space Network. In early 2020, that antenna went offline for scheduled upgrades, work that had been planned for months to keep the aging dish functional for years to come. For about 8 months, NASA could still receive faint signals from Voyager 2 using smaller antennas, but it could not send any commands back. If something had gone wrong on the spacecraft during that window, if any system had needed correction, there would have been nothing anyone on Earth could do about it. The spacecraft was, quite literally, alone, drifting through interstellar space completely on its own for the first time since 1977, with no one able to speak to it at all. When the upgrades were finished in late 2020 and communication was restored, engineers described a wave of quiet relief that rippled through the mission team. Voyager 2 had done exactly what it was built to do. It had kept flying, kept collecting data, kept being Voyager, entirely on its own without a single command from Earth for the better part of a year. There was no dramatic discovery waiting on the other side of that. Silence, no secret message, no anomaly that rewrote physics. What NASA found when contact was restored was something arguably more powerful than any single discovery could have been. Proof that a machine built with 1970s technology, using computers with a tiny fraction of the processing power of a modern calculator, could survive complete isolation across trillions of kilometers of empty space and come back exactly as it left. That wasn't the last scare either. In August 2023, a series of scheduled commands sent to Voyager 2 contained an error. A single wrong command caused the spacecraft's antenna to tilt just 2 degrees away from Earth. 2 degrees might sound negligible, but at a distance of nearly 20 billion kilometers, even a fraction of a degree is enough to send a signal missing Earth entirely, vanishing uselessly into the depths of space instead. For weeks, NASA lost the ability to communicate with Voyager 2 in any meaningful way. Engineers described it as one of the most serious communication crises in the mission's history. There was a real possibility that contact might never be restored, that the spacecraft would simply continue drifting silently forever, fully functional but permanently unreachable, a ghost ship sailing through the dark. Rather than give up, the team at NASA's Jet Propulsion Laboratory tried something they called an interstellar shout, an unusually powerful focused transmission sent, using the highest output the Deep Space Network could manage, essentially betting that if they shouted loud enough, Voyager 2's antenna might catch enough of the signal to reset its orientation and point itself back toward Earth. Weeks later, against long odds, it worked. Voyager 2 reoriented itself, reestablished a stable link, and resumed sending data as though nothing had happened. Once again, a machine designed and built before most people alive today were even born had saved itself, guided by decades-old engineering and a command sent across a gap so vast that light itself takes over 19 hours to cross it. That number is worth sitting with for a moment because it's easy to say numbers like 20 billion kilometers without actually processing what they mean. Light, the fastest thing in the known universe, the thing that crosses the 93 million miles between the Sun and Earth in about 8 minutes, takes over 19 hours to reach Voyager 2. If you wanted to send a single command to that spacecraft today and get a response back, you would be waiting nearly 40 hours round trip. Every single interaction with Voyager 2 takes place across a delay longer than most people's entire workday, repeated twice. It's not a conversation. It's closer to writing a letter, mailing it into the void, and waiting almost 2 full days to hear if it arrived. Which brings us to where things stand right now in 2026, and why the phrase Voyager 2 went silent keeps circulating, even though the spacecraft is, as of this moment, very much still alive and still talking to us. The real, ongoing story of Voyager 2 today isn't about a single dramatic blackout. It's about something slower, quieter, and in its own way more emotional. A long, carefully managed process of letting a beloved machine die gracefully instead of abruptly. Both Voyager 1 and Voyager 2 are powered by radioisotope thermoelectric generators, devices that create electricity from the heat released by decaying plutonium. When they launched in 1977, these generators produced around 470 watts combined, enough to run 10 separate scientific instruments plus all of the spacecraft's other systems. But radioactive decay doesn't stop, and neither does the slow decline of available power. Each year, both spacecraft lose roughly 4 watts of electricity, a number that sounds small until you realize it never reverses, never pauses, and never gets better. It only ever goes one direction. For years, NASA's engineering teams have been making increasingly difficult decisions about what to sacrifice in order to keep the mission alive longer. They've turned off internal heaters, even though it means some instruments now operate at temperatures colder than they were ever designed to survive. Temperatures that by all engineering logic should have destroyed them years ago, but somehow haven't. They tapped into a reserve of backup power originally meant for an onboard safety mechanism, essentially borrowing against a system that was never meant to be touched, in order to buy a few more years of operation. And one by one, they have begun shutting down the scientific instruments themselves, prioritizing which ones give the most valuable data for the least amount of power. In October 2024, Voyager 2's plasma science instrument was switched off, a device that had been providing diminishing returns anyway due to its orientation relative to the direction interstellar plasma flows. In March 2025, its low-energy charged particle instrument, which had been mapping ions, electrons, and cosmic rays since launch, was powered down as well. And now, sometime in 2026, Voyager 2's cosmic ray subsystem, the very instrument that helped scientists determine exactly when and where its twin, Voyager 1, crossed into interstellar space, is scheduled to go dark, too. Once that happens, Voyager 2 will be left with just a small handful of active instruments, primarily its magnetometer and its plasma wave subsystem, tools that measure magnetic fields and electromagnetic waves in the space around it. NASA's engineers believe that with careful power management, both Voyager spacecraft could continue operating with at least one working instrument well into the 2030s. But nobody at NASA is making promises. As Voyager project scientist Linda Spilker has put it, every single day these spacecraft continue operating in a region no other machine has ever explored is, in a very real sense, borrowed time. Every day could be their last, and every day could also bring another discovery about a part of the universe we have never been able to study directly before. Because, make no mistake, even now, even this deep into the mission, even this far from home, Voyager 2 is still doing science that nothing else on Earth or in orbit can replicate. Its instruments continue to measure the density, temperature, and composition of the interstellar plasma surrounding it, providing the first direct, on-the-ground measurements humanity has ever had of the environment between stars. Before Voyager 2 and its twin reached interstellar space, everything we knew about that region came from theoretical models and indirect observations. Now we have actual instruments physically sitting inside it, radioing back real numbers. The data has already revealed surprises, including unexpectedly turbulent regions at the boundary of the heliosphere and magnetic field behavior that doesn't perfectly match predictions, forcing scientists to revise their models of how our sun's influence fades into the wider galaxy. There's something almost poetic about the timing of all this, because 2026 isn't just another year in the Voyager mission's slow decline, it's also a year of milestones. Later this year, on November 18th, 2026, Voyager 1 will become the first human-made object in history to reach a distance of 1 light day from Earth, more than 16 billion miles, or roughly 1.08 trillion kilometers. At that distance, a signal traveling at the speed of light, the fastest anything can move in this universe, will take a full 24 hours just to arrive. Voyager 2, trailing not too far behind on its own path deeper into the galaxy, continues its own record-breaking journey as well, currently sitting at roughly 143 astronomical units from the Sun, or about 21.4 billion kilometers. To put that in perspective one more time, because it really is worth repeating, these are two machines built using technology from before the invention of the personal computer, before cell phones, before the internet, using onboard computers with less processing power and memory than a modern digital wristwatch, and they're still functioning, still collecting data, still talking to Earth, from further away than any human object has ever traveled, at speeds exceeding 34,000 miles per hour, in a region of space where temperatures plunge toward absolute zero and radiation levels are unlike anything encountered near any planet. Behind every one of these numbers are real people who have spent entire careers keeping these two machines alive. Ed Stone, who served as the mission's chief scientist from its earliest days until his retirement, dedicated more than half a century of his professional life to this single project, overseeing discovery after discovery as the twin spacecraft swept past 4 planets and then kept going into the emptiness beyond. Suzanne Dodd, the current Voyager project manager, has described the mission's engineering team almost like doctors caring for 2 extremely elderly, extremely precious patients. Patients whose original designers never expected them to survive this long, and whose remaining systems now require constant, delicate monitoring simply to keep functioning. Linda Spilker, the mission's project scientist, has spoken about the emotional weight of these decisions, the strange, bittersweet responsibility of deciding which parts of a 50-year-old spacecraft to switch off first, knowing that every choice extends its life by mere months or years at most, and that eventually, no matter how carefully these decisions are made, both spacecraft will fall permanently silent. When that day finally comes, and it will come, whether this year, next year, or sometime in the early 2030s, it will mark the end of the longest continuously operating space mission in human history. Nearly 50 years of uninterrupted exploration, spanning 4 planets, dozens of moons, the edge of our solar system, and the beginning of interstellar space itself. No spacecraft launched since has matched what these two machines accomplished. And given how rare the planetary alignment that made their grand tour possible actually is, it's entirely possible nothing ever will again, at least not for another century or more. But even after their instruments go dark, even after the last signal is received and the last data point is recorded, Voyager 1 and Voyager 2 will not stop moving. They will continue drifting outward, silent and dark, carrying their golden records into the depths of the galaxy for millions, possibly billions of years, long after every human alive today, long after every nation, every language, every structure we've ever built has crumbled or changed beyond recognition. In roughly 40,000 years, Voyager 2 is projected to pass within a few light years of a star called Ross 248, not close enough to be seen, but closer than any other star will come to it for a very long time. It will not stop there. It will keep drifting, essentially forever. A small, cold, silent artifact of a civilization that once existed on a small blue planet, orbiting an ordinary yellow star, carrying inside it the sound of human laughter, human music, and human voices saying hello, just in case, against all odds. Someone or something out there is ever listening. So when you hear a headline claiming that Voyager 2 went silent and what NASA found changed everything, understand what's really being described. It's not a single dramatic secret. It's not a hidden message from beyond. It's something quieter and, honestly, something far more remarkable. It's the story of a machine that has gone silent before, more than once, for entirely explainable reasons. Antenna repairs, a stray command, the slow, inevitable decay of a nuclear power source that's been running since before most of us were born. And every single time, against distances so vast they're almost impossible to comprehend, against a communication delay measured in entire days, against technology older than color television in some households, it has come back. It has kept talking. It has kept exploring. And for now, right now in the year 2026, somewhere more than 21 billion kilometers from where you're sitting, listening to this, it is still out there, still moving, still sending its faint, patient signal home. Whether it keeps doing that for another year, another 5 years, or all the way into the next decade, nobody can say for certain. What we do know is this. Every single day Voyager 2 continues to function is a day beyond what anyone who built it ever expected. Every signal it sends is a small, quiet miracle of engineering from a different era, reaching across a gap in space and time that still, even now, is almost impossible to fully wrap your mind around. And when the day finally comes that its last transmission fades into static and NASA's engineers, after nearly 50 years, finally have to say goodbye, it won't be the end of its journey. It will just be the moment we stop being able to hear it. There's a detail about this mission that often gets lost in the bigger, more dramatic numbers, and it's worth slowing down for because it says something about how differently we used to build things. Voyager 2's onboard computer system was designed in the early 1970s. It has about 69 kilobytes of memory across its combined computers. To put that in perspective, a single modern text message uses more digital storage than that. The spacecraft can't stream data continuously back to Earth the way modern satellites do. Instead, it stores small amounts of information and transmits it in scheduled bursts, using a radio transmitter with less power output than a household refrigerator light bulb, roughly 23 watts, aimed across a distance so vast that by the time that faint whisper of a signal reaches one of the massive 70-meter dishes of the deep space network on Earth, it has weakened to a fraction of a watt, buried in a wash of cosmic background noise that engineers have to carefully filter out just to recover a readable signal. And yet it works. It has worked for nearly 50 years. There is something almost humbling about that fact, that some of humanity's most enduring achievements in space exploration were built using less computing power than what runs a modern kitchen appliance, engineered instead with an obsessive, almost old-fashioned attention to redundancy, simplicity, and durability. That redundancy has saved the mission more than once. Back in April 1978, less than a year after launch, Voyager 2 experienced a failure in its primary radio receiver, forcing it to switch permanently to a backup system, one that itself later developed a fault, causing it to become extremely sensitive to specific frequencies and temperature shifts. Engineers on the ground had to learn to calculate the exact frequency needed to communicate with the spacecraft based on its temperature and relative velocity, a workaround that NASA has been using successfully for over 4 decades. It's a strange thing to consider that the exact same jury-rigged solution engineers devised in the late 1970s to fix a broken radio receiver is still, to this day, the only way humanity is able to send commands to a spacecraft flying through interstellar space. The scientific payoff of all of this persistence has been extraordinary, and it goes well beyond the 4 planets Voyager 2 visited on its way out of the solar system. Since crossing into interstellar space, Voyager 2's plasma wave instrument has picked up something almost eerie, oscillations in the plasma surrounding the spacecraft that scientists have been able to convert into sound, revealing a kind of persistent low hum in the space between stars, generated by the interaction of interstellar gas with the outer edges of our sun's magnetic influence. It isn't sound in the way we experience it. There's no air out there to carry vibrations the way sound travels on Earth. But the instrument is picking up electromagnetic oscillations that, when translated into audio frequencies, sound uncannily like a faint, continuous drone, an ambient noise coming from deep space that no human being had ever been able to detect directly until these 2 aging spacecraft flew far enough to hear it themselves. Some scientists have described this discovery as one of the most important contributions Voyager 2 has made since leaving Neptune, because it gives researchers an actual, measurable baseline for the density of interstellar space, something previously estimated only through theoretical models, and now confirmed through direct observation. It's also worth remembering just how much of what we now consider basic knowledge about our own solar system exists, specifically because of what Voyager 2 measured on its way out. Before Voyager 2's flyby, scientists didn't know Uranus had such an extreme axial tilt affecting its magnetic field in such a strange off-center way. They didn't know Neptune's atmosphere contained storm systems large enough to swallow Earth many times over, or that a moon like Triton could have active cryovolcanoes erupting nitrogen gas and dust particles kilometers into space, despite surface temperatures hovering around negative 235 degrees Celsius, among the coldest measured surfaces in the entire solar system. Every one of those discoveries reshaped textbooks, reshaped models used by planetary scientists for decades afterward, and in many cases remains our only direct, close-up data about those worlds because no other spacecraft has ever gone back. That's perhaps the most sobering part of this entire story. There is currently no mission planned, funded, or even seriously proposed that would return to Uranus or Neptune in the way Voyager 2 did. Scientists have advocated for decades for a dedicated orbiter mission to the ice giants, arguing that our understanding of these 2 planets remains stuck largely where Voyager 2 left it back in the 1980s. Budget constraints, competing mission priorities, and the sheer distance and cost involved have kept any such mission from moving past the proposal stage, which means that for the foreseeable future, and quite possibly for the rest of this century, the single closest look humanity has ever taken at Uranus and Neptune remains the brief flybys performed by a single spacecraft, launched in 1977, running on computers with barely enough memory to hold a modern email. All of which makes the ongoing survival of Voyager 2 feel less like a footnote in space history and more like an active, ongoing act of preservation, one final extension of a scientific effort that can never quite be repeated. Every additional month of operation is, in a very real sense, additional data that cannot currently be obtained by any other means, from any other source, using any other spacecraft, because nothing else is out there. Nothing else has gone this far, seen what this has seen, or is positioned to keep measuring what it continues to measure. Because out there, past the edge of everything we've ever charted, Voyager 2 will keep going forever, or as close to forever as anything built by human hands has ever come.